Pluto is a far-off and strange dwarf planet that was once a member of our solar system's planetary family. However, recent surprising announcements by leading astrophysicists Neil deGrasse Tyson and MIT's Michio Kaku have brought Pluto back into the spotlight with a stunning revelation. They suggest that this cold world is on a potential collision course with Neptune. Yet, how could this happen, and what might be the consequences of such a massive event? Are we witnessing a unique cosmic phenomenon, or is there more to this impending infinite impact? Join us as we explore the possible outcomes of a Pluto-Neptune collision. Pluto, a former planet that was downgraded to a dwarf planet partly due to its unusual orbit, remains a subject of interest and study in the cosmic community. According to recent predictions by leading scientists, Pluto's trajectory is alarmingly close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the red flag on a potential hazardous collision between these two celestial bodies that could pose a significant threat to Earth. How is such an event even possible? Pluto's journey around the Sun is unlike any other planet in our solar system. It takes an astonishing 248 years to complete a single orbit. This means that since its discovery in 1930, it hasn't even completed one full revolution. But the intrigue doesn't stop there. Pluto's path is marked by its highly elliptical shape, deviating significantly from the near-circular orbits of the major planets. What makes Pluto's orbit even more peculiar is its inclination, tilted at 17 degrees to the ecliptic plane. The path Pluto follows is much steeper compared to the other planets. This tilt and eccentric nature add layers of complexity to its orbital pattern. One of the most fascinating aspects of Pluto's orbit is its intersection with Neptune's path. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, defying what we might expect from their positions in the solar system. This prompts the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers struggled to understand its unique trajectory. Unlike other planets, whose orbits lie relatively close to the ecliptic plane, Pluto's path stood out with its steep tilt and elliptical shape. The mystery deepened with the realization that Pluto's orbit actually crosses Neptune's. The stability of Pluto's orbit amid these complexities is proof of the intricacies of space mechanics. The three-body problem in space deals with understanding how three objects, like Pluto, Neptune, and the Sun, move and affect each other with their gravitational forces. It's like trying to predict where they will go based on where they start and how they pull on each other. In Pluto's case, this problem illustrates how its path, Neptune's path, and the Sun's gravity all work together in a complex manner. The terms alpha libration and latitude libration, along with the VZK oscillation, are part of this puzzle. According to astrophysicists, what keeps all planets in their orbits is a phenomenon called alpha libration. In the context of Pluto and Neptune, this term means that whenever Pluto crosses Neptune's orbit, it is positioned about 90 degrees away from Neptune. This spatial separation is crucial in preventing their paths from colliding. Latitude libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is situated significantly above their orbital plane, adding an extra layer of protection from potential collisions. Another significant factor in this scenario is the VZK oscillation, named after three scientists, von Zeipel, Kozai, and Lidov, who studied how objects move in space. This oscillation explains how three space objects, like Pluto, Neptune, and the Sun, exert gravitational forces on each other, affecting how they move. In Pluto's case, the VZK oscillation helps us understand why its path around the Sun is so unique. Even though Pluto's path seems erratic, this oscillation helps keep it moving smoothly for long periods. The VZK oscillation shows that, even if things in space seem chaotic, there are patterns and rules that keep everything in order. All these factors help maintain the stability of Pluto's orbit, ensuring it doesn't collide with Neptune or veer off course. This three-body problem aids in understanding how these paths change due to the gravitational interactions among these space objects. Studying this helps us learn more about Pluto, our solar system, and distant universes with their stars. Mathematical simulations in the late 1980s revealed that, despite these stable properties, Pluto's orbit is actually chaotic, with small changes in initial conditions leading to significant differences over millions of years. However, these unique properties of Pluto's orbit have been found to maintain stability over incredibly long timescales, effectively keeping the chaos in check. Recent computer simulations have helped us understand how large planets like Neptune, Jupiter, and Saturn influence Pluto's orbit around the Sun. Neptune has a special relationship with Pluto, where, for every 2 orbits Pluto makes around the Sun, Neptune completes 3. This relationship helps keep Pluto's path consistent. But Neptune isn't the only one contributing. Jupiter's gravity also plays a significant role in maintaining Pluto's orbit, and Saturn adds to this stability as well. These simulations show that Jupiter's gravity alone is strong enough to ensure Pluto stays on a stable path for an extremely long time, even billions of years. It's as if Neptune, Jupiter, and Saturn are working together to keep Pluto safely moving through space without running into trouble. Peculiarities are fundamental in the specific circumstance of the universe for keeping up with the request and consistency of room bodies' developments. Without these instruments, the planetary group, as far as we might be concerned, would be a spot of a lot more prominent turmoil and eccentricism. Bodies like Pluto could possibly slam into others or be shot out from their steady ways, driving to a cascading type of influence on other heavenly bodies. For Pluto particularly, with talks about it perhaps colliding with Neptune later on, understanding its circle is truly significant. This gives us a more clear image of the planetary group's dynamic nature. The instance of Pluto illustrates how even the most apparently unsteady circles can accomplish a condition of balance through the complex transaction of gravitational powers and orbital mechanics. It additionally shows the significance of constant perception and investigation of these peculiarities to all the more likely handle our spot in the universe. Investigating the profundities of room frequently drives us to defy the capricious idea of heavenly bodies, and Pluto's circle is a great representation of this unconventionality. The idea of orbital disorder, which alludes to the delicate reliance of a heavenly body's way on its underlying conditions, is clearly outlined in the instance of Pluto. This implies that even slight variations in the Bantam planet's position or speed can fundamentally shift its drawn-out course. In the tremendous scope of our nearby planet group, Pluto possesses a novel place that challenges how we might be informed about planetary grouping and elements. Since its disclosure in 1930, Pluto has gone through broad review, prompting critical disclosures about its structure and conduct. Quite possibly of the most interesting element of Pluto is its surface, which is a mind-boggling embroidery of rock and different mixtures. The New Horizons mission, which flew by Pluto in July 2015, gave remarkable information about this far-off world. The outer layer of Pluto is described by enormous fields, transcending mountains, and profound valleys. One of the most prominent highlights is the Sputnik Planum, a huge heart-molded plain basically made out of nitrogen ice. This region features a different exhibit of land highlights, including enormous chunks of ice and what have all the earmarks of being streaming icy masses. The presence of these elements shows that Pluto might in any case be geographically dynamic, regardless of its perfect distance from the Sun and low temperatures. Another interesting viewpoint of Pluto is its air, made predominantly of nitrogen, with hints of methane and carbon monoxide. Pluto's environment is dainty, yet it displays captivating occasional varieties. As Pluto approaches the Sun in its prolonged circle, its climate can extend and contract. This unique way of behaving is a reflection of the unpredictable relationship among Pluto and its current circumstance. During its nearest way to deal with the Sun, some of the air gases might freeze out onto the surface, while as it moves farther away, these gases can sublimate back into the climate. The communication among Pluto and its biggest moon, Charon, additionally adds intricacy to the framework. Charon is moderately enormous contrasted with Pluto, with a width of about around 50% of that of Pluto itself. This size proportion implies that the two bodies are in a shared circle around a point in space that lies between them, instead of Pluto basically pivoting around Charon. This interesting relationship adds to the multifaceted gravitational elements in the area, affecting the circles of other objects in the Kuiper belt. The Kuiper belt, a district past Neptune populated with little frigid bodies, is home to numerous other Bantam planets and potential impactors. This belt is a repository of old material from the early nearby planet group, furnishing researchers with a brief look into its arrangement. Pluto's orbital qualities could offer experiences into the relocation examples of these far-off objects, proposing connections with bigger planets that may play a vital impact in forming their ongoing circles. One of the key ramifications of grasping Pluto's orbital elements is the expected effect on our cognizance of the Sun-oriented framework's development. The gravitational impacts from neighboring Goliath planets like Jupiter and Neptune can adjust the directions of more modest bodies, including those in the Kuiper belt. Such communications can bring about shifts in circles, possibly prompting impacts or on the other hand launches from the planetary group. As specialists keep on investigating the subtleties of these communications, they may uncover more extensive examples that administer the conduct of heavenly bodies all through the cosmic system. The investigation of Pluto too brings up philosophical issues about grouping in cosmology. The choice to rename Pluto as a Bantam planet in 2006 was dubious. Lighting discusses what comprises a planet. The International Astronomical Union's definition zeroed in on an article's capacity to get its circle free from flotsam and jetsam, a standard that Pluto neglects to meet due to its vicinity to different articles in the Kuiper belt. Anyway, the intricacy of Pluto's circle, its geographical action, and its climate show that it is undeniably in excess of a straightforward frozen rock on the edges of the nearby planet group. These perceptions challenge conventional astuteness about planetary characterization, provoking conversations about the developing nature of how we might interpret heavenly objects. The term planet itself has moved in significance throughout the long term, mirroring the extending skylines of human information. As we test further into the secrets of Pluto and other far-off universes, we are reminded that our comprehension of the universe is ceaselessly advancing. The once disputable renaming of Pluto as a Bantam planet was only one stage in a continuous course of revelation, where new information continually challenges our biases. With each new mission to the external compasses of the nearby planet group, we inch nearer to unwinding the intricacies of these far-off domains. Pluto's tumultuous circle, its communication with Charon, and its job inside the Kuiper belt offer significant examples for researchers looking to understand the